see this might be working. So I started, but the mic has some issue here. But maybe hold the mic for the moment. Hope that now works a bit. So we have done our first part of the course, which is going to be, if you recall, our course outline. So what we have covered is what we so-called the part A of the syllabus. We have done the individual and the equilibrium idea. We're going over the consumer. For preference, utility demand, production, it will be profit and cost. And we also study how market works. And we assume that consumers are price taker, right? And the firm are price taker as well. So they are not big enough to manipulate, right? Or there's not too much gain from being strategic. And in that case, what we have studied would be fine, right? It fit very well for financial market. But then within firm or in business, we know there's some strategy can help. So for the second part of our course, which we will talk about game theory. And game theory, we will focus on non-cooperative game theory, which is the dominant one, although it's not the earliest one. The earliest one is what we learned, the core idea, the core allocation, that idea related to that. But the more modern one is this style. And you try to give a foundation how they work, right? So imagine this is non-cooperative is more like micro level. You go to very detail how people make decisions. But when we talk about general equilibrium type of core, we talk about Pareto efficiency. It's more like the macro style. So like one is more like the structural form, one is more like reduced form. And you can't say one is better than others, right? You have different assumption, right? I mean, the cooperative one is like you have make less assumption, right? Likes to hold more general. And the non-cooperative one is going to be more specific, right? You deliver more specific result. It's good if your model fit what it is. It doesn't work very well if your model doesn't fit very well. So it's not more micro and macro approach or reduced form or structural form approach. It's hard to say which one dominate, but this day, I mean, we would be talking about this because it's a non-cooperative one is more popular because it is pinpoint how things changes, how the situation changes, the way you behave. Okay, but anyway, let's go directly. I mean, we talk about today will be study games of complete information. If you learn game theory, this class will be easy because we are not trying to introduce you any new concept, but rather we review the style that are more rigorous. So everything will be compared to undergrad, we'll talk things in the form of more rigorous version. Okay, hope that will lift you up to the PhD level. So let's get started. Okay, study game of complete information. So but the topic here, we'll talk about game theory first. So as we said, this is what usually covered in US or in Europe. This is standard course of game theory. We will cover all this for. And if you go to econ department, basically spend whole semester for these 4 topics. Okay, so you can imagine that I should have spent at least 3 weeks for each topic. But the time we have, we only can spend 1 week or a little bit more, but I think 1 week is sufficient for our purpose. But fair enough to say that a lot of complication I skip. I just mentioned because we do it without proof. If you go to the econ department, they'll do all the proofs. Okay, but don't worry. I mean, now I think if you just apply it, I don't think you need those skills. You just need to know how to write the game, how to solve the game. Okay, and the important point is not solve the game, but rather how to write the game, because AI is able to solve the game very quickly, right? I mean, the AI is so smart. So the problem is now still AI doesn't really know how to make the game. I mean, even AI still, I mean, AI still may not be able to set the game correctly. So I have to be very careful. So there's a game theory well known. So the main book, you can take a look. In particular, I recommend you to read the very first item, which is only like 20 pages. That will cover the most of the things we discussed in this class. Okay. And I also recommend you would read the second and third one, which is a little bit more advanced. Once you finish the first item, you want to put in the IO. Although you're a business school student, then IO is most closely related application that you can relate yourself to. And then if you really want a textbook, recommend the Gibbons, which is the undergrad master level textbook. But that book contained exercise and material that, I mean, you would be enough for you to review. Okay. And also there are other textbook, the IO textbook, the game theory textbook also will be working. But of course, if you want a one step further, then probably you want to take the Thoreau and Fildenberg game theory textbook, which will be the PhD level game theory one. These are all the more like master level. If you really want the PhD level, then you should do those. But only if you handle some technicality, some something existent, something like large continuity, those kind of special cases. I don't think this will be sufficient for the most purpose. And I think that would be enough for our class as well. So just a motivation, because study the market. So game theory is the best way to try to model market. And that starts from the idea of we study the two type of model, right? The monopoly and perfect competition, right? Monopoly is the firm is the only seller, then he can decide where to pick in the demand curve. And perfect competition is the case where no agent is able to change the market, so everyone is taking what happened in the market, right? And in the market problem, formally you have production level big Q and the inverse demand function P of Q and cost function C of Q. They'll give you the objective function, and where the firm is choosing a quantity on the demand curve, okay, or inverse demand curve to maximize profit. Okay, and in this case, consumer is really not doing anything. It's not responding. It will be good to do it. Maybe in these days, I think those of you from information system, platform, they actually said this, right? Consumer are not really changing, right? And so the this model, right, just very simple, right? You don't talk about any. The consumer can be summarized by a demand function, right? So it's not in terms of game theory, it's not a player in the system. There's only one guy doing decision, right? So the player is very simple, right? We simplify that, right? But do note that even monopoly, we need not have this kind of assumption, right? And because the consumer can do things other than this, right? Even if you consider discrete choice model, the consumer have outside option, right? And these are rather important in that sense, right? Because the upside option can be affected by how much people are doing, right? In terms of if the network effect, you have externality for the consumer. Okay. So if you're perfect competition, you have n firms, and you do see that the total production in spec Q depend on each firm's output, and each firm's output depends on its own production, right? But also the total, right? But the thing is that consumer would take the other industry production, right, other firms' production, industry production as a constant, and he's not moving the industry output. Then in that case, right, if you maximize thinking this spec Q a constant, okay, just thinking, okay, he's thinking that no matter what he changes, QI has no impact on Q, right? And this become optimization, right? You don't really rely on all the QN, right? In terms of math, right, it just means the partial derivative of Q, spec Q respect to your QI will be 0. Right? Just by assumption, right? Because the firm is solving this problem, right? And if you take the FOC, right, which is the partial derivative of pi respect to small qi, and if big Q over Q is, say, if this guy is 0, right? That's perfect combination, right? This, you may ask why this would hold. Well, if you think this is the case, then it will fine, right? If you think in this way, behave as if perfect combination, that's fine. Okay, it don't have to be really has no impact, but if you think there's no impact, everyone would do it the same, and that would be fine. Okay. Now, I guess that is, as I said, the more important is like these days is we're few firms in the market, right? Like especially in new economy, look at the platform, say look at the food delivery. You have Kita or Food Panda. Is it Food Panda? They still exist? Food Panda, right? Because I didn't use it, so I don't know. But if you use taxi, then probably now you have Uber or DD or right or some others, right? You have very few. So if you have few number of firms, then it will be important to model how they behave, right? And just like if you're from accounting, then you know Big Four is so big, right? It's basically majority of people are choosing Big Four to do auditing service, right? Same as stay in school, right? We only have 8 university in Hong Kong, right? So you have a limited number of competent. Although you may have a lot of school in China, but look at 211 or like 5, right? Or double, I don't know, excellence, right? Shang Yi Liu, right? That is a really limited number of. And in that case, game theory is a good way to model, right? Because the thing that game theory is good at is you don't take the other guy's action constant. You do notice that what you're doing would affect others, and what other may do would affect you, and you have to think what they have been thinking, right? And they have to think what you're thinking, and they have to think you have to think what they are thinking about your thinking, right? So you have to keep thinking this loop, right? Just like you play chess, right? You have to think not just this is the best move in this round, right? But you have to think about next round after next round, right? So you keep thinking about that point, right? Just like you're doing the rock paper scissors, right? You have to think about what's the best depends on what other you're choosing, right? There's no single strategy no single action that is the best. So that it really depends on the type of the others, right? On what they're choosing. So that is the operative problem, just very simple motivation there. If you're firm 1 and 2, right, the production cost CI, right, this firm 1 will be this product function, and firm 2 this product function, right? Then you can notice firm 1 payoff depend on firm 2 choice, and firm 2 depend on firm 1, right? And the problem is how to solve this type of problem. Okay, it's not clear how to solve this problem, right? Because how should I choose, right? My choice or my best choice depend on what you're doing, right? It's not unlikely then what is the solution there? What would what's the prediction, right? If you do low, I may do high, do high, I may do low. What is the outcome? Just like rock, paper, scissors. Do we have anything to say, right? Of course, if you do rock, I will do paper. If you do paper, I will do scissors. If you do scissors, I will do rock, right? But the problem is, without knowing what you're doing, what should I do? You should tell me what should I do, right? I mean, or what should be the outcome, right? I mean, that is the problem thing, okay? And as we said, there will be four types of games that we will study in for different topic. Then it actually depends on the timing. Whether static means everyone interact once and for all. Okay? When you make the decision, you don't know what other people doing. Okay, and they just come out at the end. They solve. Don't have to static doesn't mean that they do it at the same time. They just look at some of the books that in undergrad they call simultaneous, but it's not simultaneous in the sense that they have at the same, they are the same. Just when they decide their action, they don't know. Just like auction, a sealed envelope auction, you put what your bid in an envelope, right, and send it, mail it to somewhere, right? They didn't actually write together, right? They just mail it, right? They just do it and send it out, right? Then it just like when they make decision, when they write the number there, you don't know, right? Or you do a voting, a mail-in voting. When you vote, you don't know what the other guy choose, right? They don't have to vote at the same time. So static doesn't mean the same time, just mean that when you make the decision, the other guy doesn't know, okay? And the other guy doesn't know what you're doing as well at the same time, okay? Dynamic in the sense that we just drop the assumption of they do the same time, okay? You might or might not observe other people have done, okay? We just sequential, okay? This is the idea, okay? And here is, I think that's even more, this is more important, is complete formation and incomplete, okay? Complete means that everyone knows everything, okay? And the other case, incomplete, is someone doesn't know, okay? And someone is not known, then problem is how to solve this problem. This is very difficult, right? If you don't know, then how do you act, right? If you don't know, you're supposed to rock, paper, scissors, right? But you don't know the other guy what he's doing, then you're not even sure you're playing rock, paper, scissors, right? Right? They may come up with something crazy, right? If you do rock, paper, scissors, they take out a knife or take out the gun, then you don't know what they're doing, right? So you are not even sure what the game is, right? Then how to solve this problem? That is complicated, okay? And later we will say, instead of incomplete, we'll focus on the model of imperfect, where you don't have, it's more like uncertainty idea, right? You have different state of the world, you just allocate different probability, and that would allow us to solve this problem. Okay, this is invented by Haase and me, but we'll talk about that later. So we focus on the static game theory, which is studied by, started by Norman Morgenstern, right? And I mean, early, of course, Connaught, but after it's Nash idea that takes off. Okay, of course, in the meantime, there are many people contributing, but these are the big guys there. Okay. So it's very important, although it's very simple, in game theory, you have to define everything properly and formally. Otherwise, you don't really know what you're doing, okay? The first thing to say would be you have to fully define the game they're playing. And in the static model, the simple game that there's only 3 guys. The first one is player set. It's very important. Who is in the game? Okay, who is being strategic? Okay, in the monopoly case, only the firm is moving. Only the firm is the player. Okay, player is the one who makes the decision. If not make the decision, they are dummy or they are not. Dummy means that actually dummy player is not really the guy who is working. So you have to be very careful. What the players are? The consumer player? Are the firms the player? Are the supplier the player? Are the government the player? Okay, you have to be very careful who are the players and who are important, right? You can't left out someone who's important in the game. Okay? But But don't add everyone there, otherwise your model will become not solvable, too complicated to solve. So the easiest, of course, is to focus on the situation where you think is important. But do remember, you have to specify everything, okay? The second one is also very important, is what action can be taken, okay? And that has to be a little bit careful because of if your action is discrete, ABC, or do or not doing, all right, to be or not to be, to do or not to do, then it's easy, okay? This discrete choice. But you have to be very careful what might be if you allow continuous, okay? Do you allow endpoint or not endpoint, okay? Or you allow continuous set or some jump set, okay? It's one dimensional or multi-dimensional, okay? That is very important, okay? And because they take action together, right? And there may be some constraint that if one take this action, that take the action, then maybe end up with something crazy. Okay? So you have to be very careful about the set. And of course, at the end is the payoff. Okay? The payoff, as you can see, the function you define later means that you have defined this function, this payoff for all possible combination of strategy. Okay, you can't say you have to say if you do rock paper scissors, you have to define each agent and every combination of rock paper scissors what's the outcome. Okay, you cannot just say okay, this is the equilibrium. I just taken this action, and usually you don't have this problem when we have talked about static. Okay, about dynamic games, then probably you would omit a lot of action payoff. In particular, if something is stupid, okay, you don't write down the payoff once stupid thing has been done. Okay, but later you will see when do something stupid, you still have to define the payoff for every possible action that can be done. Okay, so that's a payoff is a function. So, but for the moment, I think for this topic, I don't think there's an issue. You just define three of things. Okay, and very often when you write papers, when you also read paper, make sure that you see three of them. Okay, you define for them. Need not be formally, but at least it's clear from your definition. Okay. So here player set. Let me maybe make it. I mean, should make it full screen. The player set is a capital N. It's 1 up to N. Okay, and in our model, we have a finite number of players. Okay? The reason being that the infinite number of players will cause some trouble. Okay? And probably you would ask one immediate question would be, what happens if consumer, right? Consumer, you have infinite thing, but you can imagine there's a represented consumer, then can make it easy. Right? And infinite is fine, but infinite has some issue there. Okay? Most of the result would hold when you go to infinity in our case, but there's some issue about existence. But I think that is okay for our major application. Okay. And if you want to write, if the operator your firm 1 and firm 2, your oligopoly n firm usually just write 1 up to n. So either use a firm 1, firm 2, or just write 1, 2. Okay, just number. Okay. Or if you like, sometimes the F1, F2, this is the way usually people write, right? This is firm 1 and firm 2. And okay, this is the way you write data set. And strategy, usually you would be writing as a generic element is SI, the set is big SI, okay? And that's usually a Euclidean space, maybe one dimension or multi-dimension, okay? And in discrete will be 0, 1, 2, 3, right? And continuous can be any non-negative number, okay? And sometimes the boundary 0 can be issue, okay? And if this is this without bound, right, without infinity, there's sometimes can also be issue, okay? So usually you may restrict to 0 up to a maximum number, right? Say x bar, okay? Then later you see this, you restrict this. X bar consider capacity of the firm, right? Or maximum that people can consume. I think you can do without loss of generality. Okay. Then your model should be more tractable. Okay. So by strategy set means that you have strategy for each player. Okay. So for example, you don't have to need to impose the same restriction of the player. S1 can be different from S2. So maybe say in this case, F firm 1 subject to constraint capacity of 10 and firm to 20, then you can just write this. Okay. Now, once you have that, that's to emphasize what is the payoff function. Payoff function is a mapping from the set of strategy to real number. Okay. But to define easily, a strategy profile is a vector of payoff, vector strategy. Okay. So what each player have chosen, okay, and this set of strategy profile, okay, is called capital S. Okay, so that means that payoff function means what? You tell me what each agent is choosing, I'll give you the payoff function. Okay, and this payoff function is a utility. So we already assume at this moment we don't start with preference. Of course, we can do preference, but just make our life easier with some payoff. It's no needed to consider ordinal or cardinal utility at this moment. It's okay to be cardinal, this utility, or can be ordinal as well. Okay, and we didn't take a stand here, but I think in most applications we just still make it cardinal. But it's okay to move ordinal is still fine. Okay, and we usually write this SI of the strategy profile will be the payoff of SI under S. Okay. Now we are equipping ourselves, and that's why look at all the textbook. A normal form game will be written as 3 elements there. You have to specify. First, specify who the players, and what they can do is SI, and what might be result if player choose this particular strategy profile. Okay? And do note that, just to remind again, the payoff function is a mapping from the strategy set of strategy profile to real number. That means that the payoff function have to be well defined for everyone and for every possible combination of action they are going to take. Okay. Once we know that, then we can go directly to the example. Consider case of 2 firms. Then N is just 1 and 2. And here we make the case they can produce whatever quantity, right? So it's a real line, okay? And allow only positive, and including 0, so non-negative. The payoff function is just the profit, right? And here just depend on the quantity and the cost. And here is the inverse demand function. Okay. And in this one, my write this, consumer is not a strategy. So it's not a player. It's not strategic. The consumer here just follow the inverse demand function. Okay. And here we also assume by cost here, we assume all the supply chain, right? It just means that the labor or capital or the bank or accountant, auditor, everyone is working for the firm is summarized by this CI. There's no firm is within firm problem here. Okay? Of course, you can open up that box as well, but in this model, we only focus on interaction between firm. It only consider the quantity, right? We just assume everything's not there. They focus on quantity interaction. Okay. Now there are, for the break, I want to talk about probably two, at least two, solution concept. Okay, the first one is dominance. And you will wonder why I talk about this before the NASH, because NASH is the most famous, as you might have learned. Why? Because dominance is a weaker solution concept. And in every model we learn, we just there will be many type of solution concept. What we learn is the major one, and we want to demonstrate that there are more than one solution concept that is good. Okay, and this is so weak that you believe that this is the result, that if this doesn't hold, then you have no hope for humanity. Okay, so this is so simple. It means that no player should choose a strategy that is always worse off, no matter what other people would do. Okay. So definition: if you have this strategy, SI is worse than SI had. Okay. It means that no matter what other guys would do, SI is worse than SI had. Okay, strictly worse. In that case, then you would not be doing that. Okay, formally is like the following. Look at, we fix a player I, okay, and for player I, a strategy SI is worse than, strictly worse than, it's called strictly dominated, strictly worse than. Another strategy as I had, if for all, okay, for every possible thing from other people might have been doing, for, okay, it must be the case that the strategy without head is worse than the strategy with head. Okay, and that means that there would be no scenario that you would choose the head one, right? Because, sorry, you choose non-head one, right? Head is always smarter than the non-head, right? So there's no way that you would do in this way, right? So at least unless the guy is crazy, right? We call it rational, you will maximize payoff, right? So there's no reason for whatever in this one-shot game you would choose a strictly dominated strategy. Okay, so I do notice that there's a very technical thing here. When we look, if you change to this less than or equal to, okay, it is not always true that the weak dominance is something we want. Okay, because something is equal but sometimes worse off. But if you think that it's still okay, right? It doesn't contradict your idea, right? You can't show this is wrong, then you may don't want to apply this. Okay, and because applying this is actually pretty strong. Okay, this is the very weak one. I guess in the experiment, I don't see anyone would choose a strictly dominant strategy. Okay, that is something I don't think anyone have experiment results. So this is case. Dominant solvable. Okay, so if no player is taking any strictly dominant strategy, and at the end, once you take out all these strictly dominant strategy from your strategy set, you only have, every player only have one outcome, then the game is dominant solvable. Okay, and let's see this very famous example then with a break. I guess everyone would have learned it if you ever touch game theory, right? Personal dynamo. So this famous game, just make it short, right? But we know it. The story is like the two criminals, right, was caught in front of the bank with guns in their car. Okay, so if the police, right, because they didn't rob the bank yet, right, so they just try to see if they would confess, right? If no one confessed, they would just send him to 1 year in prison for just illegal ownership of the gun, right? Because you didn't show, they didn't rob the bank yet, right? So none of them would go to jail for a very long time, just for 1 year, for illegal possession of guns. Okay. But if both of them actually said, okay, we are actually robbing the banks, right? Then they go for 6 years for because robbing the bank, right? But of course, because they are confessing, right? They are honest to the police, those they get some deduction of the offense, right? But if one said to the police, but the other keep their mouth shut, then the one who is not telling the police will get 9 years. The other guy go free because as a bonus or reward, right? And usually, I mean, then the police try to detain them, they will separate them, right? Because they don't allow them to collaborate, right? You will see if they are allowed to collude, then they will not. The outcome is different, right? So that is what we mean by non-collusion theory, is they make decision separately, okay? They don't know the other guy have chosen. So look at this question. So we will use this table to illustrate how we write the game. Remember, there are 3 elements in the game. 1, player set. Where you can see the player set is here, 1 and 2. Okay, this is a player set we write down here. Second, strategy set. Player 1 has access to 2 strategy represented by the number of row, and the row we have C and D, so that is the 2 possible choices. And you have player 2 have also 2 possible strategy. And the last thing is payoff function. Telling us what is how much utility they will get for each possible outcome, right? Outcome is the strategy profile, right? So they choose C and C. Player 1 get -1, player 2 get -1, which they go to jail for 1 year, right? So C and D, they confess, right, to the police, and the other guy didn't. So if you, in this case, C is mean collaborate, means that they do not tell the police, they remain silent. Okay, it's corroborate police. Okay, so the corroborate police, then we get -1. Oh, I guess I get the wrong one. So I think C here, I said they corroborate each other. Let me rewrite the C means collaborate with each other. It's the effect from the other guy because they are the group. So the collaborate means that they keep their mouth shut, and D means the defect means they tell to the police. Okay. That's still okay. So if the other guy tell the police, if you don't, they get negative. You go to jail for 9 years, the other guy go for 0. And reversely the case, and if everyone tell the police, everyone got -6. Okay. So if you study game theory, how to analyze this game, and this game will be simply, it's easy to check if there's stable strategy, okay, and then we'll take it out, okay. So yes, this is stable strategy. So look at this. If you consider your player 1, okay, you're choosing C or D, okay, you are telling the police or not, okay. So suppose the other guy choose C, okay, the other guy tell the police, what should you do, okay? If you tell the police, right? If you choose collaborate, you get -1, right? So you go to jail as well. Maybe I made mistake here. Let me check. If okay. If I don't tell, if the other guy don't tell, I get 1 year in the jail. Okay, yeah, that's right. If the other guy don't tell the police, I tell the police, I get 0. So this is better, right? So if the guy don't tell, it's better I tell, because if I don't tell, I go for 1 year. If I don't tell, if I tell the police, right, then I defect, I become a bad guy, then I go have no time in spend in jail, the other guy go for 9 years. Okay. And the other case is the other guy tell the police, okay, if I remain a loyal to my friend, then I actually go to the jail, he go for free. If I also tell the police I got 6, so this D is better. Okay, that means that telling the police is always the best, no matter what you do, right? If you don't, I tell, then I have 3. If you tell, you would tell, then I tell, we get some deduction, right? So it means that regardless of what you're doing, D would be the best, right? So that's why the police would separate people, because no one will be choosing C, right? In that case, because choosing C is something stupid, right? No, there's no reason you would choose C, right? So the only outcome you get is just DD, right? It's defect and defect, right? So this doesn't require you to do any analysis, right? As long as the assumption for this is just like you believe the other guy is not stupid, okay? And I'm not stupid, right? And no one's stupid, then this outcome, right? Don't require to guess what they're able to do, okay? So that's why it's the strongest prediction you would have expect, right? So this is we call dominant solvable, okay? And you try to make sure that no-brainer, this is the easiest, okay? This is the strongest result you can get, okay? And you may try to see this is very interesting, right? Because even though they're strategic, the player, if they're smart, okay, nobody's stupid, then this is the outcome, right? And it also imply that if the managerial constraint is, if you want some outcome, even they're strategic, you can decide the incentive such in the way that this is the outcome. And this is, if at time we talk about contract theory, or we talk about mechanism design, this is something that we are striking for, right? We want that regardless of the strategic environment, right? Something that's best for you, and you want this to be happening. Okay, and that is similar. Actually, later you see the contract theory is like this. I don't know what they may have done. Okay, I will design the environment system such that, okay, players would just do as I wish. Of course, this is not designing, but actually the police is deciding the game in a way that they separate each other, right? And then they would just have to make a decision without the other guy knows, right? And that's the reason the mafia, right, how they can sustain collaboration is by using violence, right? Or you have your family, right? You have some rewarding system, which we'll talk about later, with the game. There's some way to get it back, right? And that is something we'll talk about next week or after. We'll talk about, actually, we will try to avoid this bad outcome. Okay, this is everyone destroying each other, right? So there must be some way that we go back to here, okay, to collaborate. Okay, and that's what happened. We also mentioned, right? C is you study. Oh, sorry, C is you don't study, you lie down. Okay, D is you study. You go to involution, right? Right. So if the other people don't study, right, you want to study, right? Then you just increase your marks, right? So you get into good school, right? The other guy don't study. That's okay, right? But if both of people study, right, then what happens is you just increase the admission bar, right? So that's what they said, right? 如果你读书，你就提高你的分数；如果大家一读书，就积极提高分数线， right? So that is what happened here, right? Just right because everyone 996 end up here, right? That is what happened, right? But the problem is how to avoid 996, right? How to avoid that, right? That's coming from what we call labor union, right? There's some way that they go together, right, to counter the capitalists, right? To see that's what he said, right? All the poor, all the no money people collaborate each other, right? 所以就说全世界的无产阶级团结起来, right? That's what happened, right? Anyway, we have a break of 15 minutes and we'll continue to talk about after that because of we talk about Nash equilibrium because not all the situation will have this nice, easy solvable one. Okay? We talk about more complicated thing. Okay, it's no longer as obvious as one action, right? Just like rock paper scissors, we don't have that, right? So that many situations this can't be done, but there are many cases this is good to understand why we end up like this. Okay, no people want to do anything, right? People just wait, and you have to take a big courage to go to there, right? And that's why, sorry, one more point is why you would have leader, why business, why management. Management is trying to move from here to here. Okay? The management using different way to design the system such that people work with each other. But I will talk about that later as well. Okay, so let's a break of 15 minutes. In the meantime, I guess I should open the you reply in case you want to say. Okay. So if you have any question, let me know. Let's resume 10:36 or 37. So let's see anything say. What's capital S and okay. Without the subscript, it means the vector. So let me go to them. There's a question is slide 17, right? So without S, actually I think I should bold it. You should put both on means without the I means a vector of all the list of everyone. Okay, and small and large, the capital one means the set. Okay, SI is the big SI is clear I's set of strategy, and big S is everyone. So maybe easy to see in this way. So in this case, okay, maybe easier to the this example. Okay, S will be something like this if you write formally. This is the formal one. Okay. S1 can be say like 10, S2 can be like 20, right? And that is how small s1 and small s2 can be any number which is s1 s1 is 0 to 10, and then small s2 is any number between 0 to 10. Okay. So big S is the Cartesian product between the S. Okay. And why? Because you would the pair function have to take one thing from 0 to 10 and one thing from 0 to 20, and then tell you what's the payoff for each firm, right? So that's a pair function tells, right? I hope that part is more clear. This mic doesn't work. Maybe I should bring my own mic next time. Okay, let me hold the mic. Otherwise, seems to be. Oh, maybe it's still okay. Okay. So this is the first question. I hope I answer you. If not, then please remind me. Okay. Not equivalent. As I said, SI is a particular element, and small SI is a one particular strategy, and SI is the set of strategy they can choose, is what they can choose. Okay, and what is actually chosen. Okay. Is it? Okay. It's partially cloudy, partially sunny, so that's right. Yeah, prisoner dilemma, yeah, that's right. And strict dominance, although that's very simple. And overall it's okay. Okay, that's good. Oh, that's good. This first time I look at this is because I go to undergrad. The graph look like this. The graph look like this. And more than 50% of people said they are super tired. Okay. And now we have a nice case. Everyone is not too tired. That's good. So I go to the master class, I go to the undergrad, they always, as a exponentially increasing. I mean, more than 50% of people say they are tired, no matter which class. But we are good. I mean, everyone is not very tired. Or you guys are very good at involution, so there's no problem. 你们很会卷，所以没有问题。But anyway, so the next is not complicated, but just keep applying strict dominance. Okay, so you take out something, and once take out, you can further take it out. Okay, and you keep delete until you get one outcome. Right? If you can do that, then that is what we call iterated strict dominance. Okay, but this is pretty strong because strict dominance only require you to know you're not stupid, and you know the other guy not stupid is fine. Okay, this is only not very strong. Okay, but you have to know the other guys know you're not stupid, right? For this one, because we have to keep doing this operation. Let me show you the example. Okay, so we are solvable means there's no outcome. So let's see example there. Okay, so look at this case. Okay, and look at first we say R is strictly dominant by C. Why? Because if one choose U, C give 2, I'll give 1. Okay, and if one choose D, C give 1, I'll give 0. Right? So R should never be chosen because R is always well. There's no absolute no reason why R is being chosen. Right? Right. But if that is it, this is done because we can't do anything more, right? So this is not dominant solvable, right? In this, it's over, right? So we still have the prediction we get is one of the 4 outcomes can be, but we don't know which one is more likely, okay? So there's not much can proceed, right? But suppose, okay, player 1 knows player 2 is not stupid, okay? And player 2 is not stupid, okay? And that means that player 1 would know player 2 is not stupid. That means that he can safely forget about how it's being chosen, right? Player 1 know player 2 is not stupid, right? That means that he would only consider player 2 is going L and C, right? He's not going to think about how it's not possible, okay? Player 1 know player 2 is not stupid, okay? That means that he would never choose D, right? Because the reason to choose D is only if player 2 choose R. But player 2 is not stupid, and player 1 know player 2 is not stupid, and R will never be chosen. That means that D will never be chosen as well. Okay? And if that is what they know, the prediction still, you have 2 outcomes. Okay? But now if player 2 know player 1 know player 2 is not stupid. Okay? In that case, okay, player 2 would be safe to say, okay, D is not chosen. Okay. And of course he's not stupid, he will not choose R. And then, but player 2 know player 1 has already known player 2 is not stupid. So that means that L will not be chosen as well, okay, because player 1 is not going to choose D, right? And player 1 can just think about U is the only thing player 1 is doing. So this is the only outcome. Okay, so if you can eliminate and end up with one result, and that is possible. And of course, this is very strong, and usually you don't see this. Okay? And usually you don't have the strict dominance, and you have the weak dominance. Okay, and of course, weak dominance has some. If you eliminate like this, there's some issue. You would later you see you kick out some of the Nash equilibrium. But if you do this, Nash equilibrium will still be there. So there's no harm always to do this. Okay. Of course, it still require you to think everyone is okay, right? And if it's complicated, then you will not see this happen. Why? Look at chess or golf, they're very complicated, right? But then if you look at this, there will be something sort of dominated, right? But people still do it, right? When you play chess, right? Because it's complicated, you don't really can't see it clearly what's going on. Okay. But anyway, let's see. This is the you can solve this model in this way. And if you look at this example, nothing can be done. Okay. There's no strategy that is strictly dominate over the other, right? So look at this example. So suppose you compare U and M. Is there any case that U is always better? No, right? Because U is still better when C is chosen, and M is better when L is chosen, right? And you want to compare M and D as well, right? Is there any case that M is always better? No, because when R is chosen by player 2, D is better, right? But when L is chosen, M is better, right? And also you can look at U and D as well. You can see if you can do the same operation, then you can see nothing can be done. Okay. And nothing can be done means what? We're not doing anything, right? So what have we done, right? There's nothing we can say. Okay. And here comes, we have a no solution, then what happened? We invent new solution. Okay. That is coming from Nash. Okay, we'll call Nash equilibrium. Okay, we're stuck here. So what can be done? Okay, of course, we have to go forward is to introduce a better solution concept. Okay, and this solution concept would try to help us to ensure that in many of the models exists. Okay, otherwise this solution is not good, right? Because this is very good solution, right? If it exists, then it's a good one. But we want to try to make it easy. Okay, make it whole. So Nash equilibrium, okay, as you can imagine, is by John Nash, right? And the idea is super simple. It seems it just say a strategy is profile stable, right? If no player want to change by himself or herself, okay. So that means that given other people will doing, okay, and no one wants to deviate from that, okay. So the definition like this: a strategy profile means everyone pick a strategy, okay, such that it's a Nash equilibrium. If for each player, okay, for all other strategy, what this equilibrium strategy with the star one better than the other one, by thinking the other guy is not changing. Okay, the other guy is still keeping his star strategy. Okay? Everyone holding star strategy, you need to check whether a player want to go away from that. Okay, so this is how you would see and profile is an equilibrium, is to go for every player, check if there's another one that do strictly better than what's supposed to be. Do you know that we don't check everything? We only check other guys are keeping the star. So we don't allow what we call joint deviation. We only allow single deviation, which will be clear a little bit later. Okay. So the first thing is what we call pure strategy equilibrium doesn't exist. Why? But later you see rock, paper, scissors actually doesn't have a strategy that would be right, because if other people choose rock, right, then I would choose paper, right? If I love the paper, I'll just draw, right? Because everyone want to keep changing. There's a cycle over there. Okay. Later we'll show you why it does not exist. And there can be more than one. Okay. It's not unique. Okay. There's a problem because unique means that you first doesn't exist is a problem. Okay. There are some cases will exist. We have shown some example to that. And it's not unique. There's also a problem because when you're more than one, then what you're going to choose. Okay. You're going to choose something. We have to make some refinement. And also the problem, of course, this is something that very important, right? It's what John Nash taught in his movie, right? Basically, in Adam Smith, we said everyone doing their own selfish stuff is going to maximize social welfare, right? This is what the first welfare film said, right? And what John Nash said, right, in this Beautiful Mind movie, is not the case because if later you will see Nash equilibrium, there are a lot of them pretty inefficient, which means that potentially, if they act on together, if they collude, they collaborate, then it's good, right? That's actually come from personal dynamic, later you will see. Okay? And that imply if people are strategic, first welfare theorem is gone, there will be some market failure problem. Okay, but we'll talk about that in the next couple of slides. Okay, the first, this is matching tennis problem, but this is what we call game theory version of rock paper scissors. Right. So this is I think it's 黑白配 something like that, or 掌心掌背 something like that. Okay, so what it is two players took a coin from his pocket. Okay, if the pocket have two sides, head or tail, right? If the coin both of them take out is the same face, either both head or both tail, then player one win $1. Okay, and if they're different, then player two wins. Okay, so imagine you take out $1 from the pocket, okay, and whether you take it out in this face or tail. Okay, and you can easily see that there's no strategy profile is Nash equilibrium. Why? Look at head-head. Suppose this is a Nash equilibrium. Okay, if head and head, of course, player one is losing because of if the money is different, right? He's losing $1. So he would want to jump down to tell them the tail, right? So this is not a Nash equilibrium because player one is losing money, right? Because they're different. Different means they're the same, right? The coin is the same. So player one actually want different, right? So he would want to deviate, okay? And look at the other case. If tail and head, right? And player one is winning, but player two say, no, let me change it if I can change, right? So there's no Nash equilibrium in this outcome, okay? And we need to check the other outcome here. Is it Nash? The answer is no. Why? Because they're the same. Player one want to be different, right? He want to jump up. Okay. And finally, if you can see, is this Nash equilibrium? Again, the answer is no, because the coin is the same. Player two want to be, so the coin is different, the player want the same, so you jump back. So you can see the cycle over there, right? Is want to go counterclockwise, right? So everyone, there's some time that want to deviate, okay? So there would be no Nash equilibrium in this particular case, okay? And in fact, this is what Nash said. I mean, instead of thinking about pure strategy, later we argue that they will randomize, okay? They would toss a coin to decide whether it's head or tail. They randomize half likely head, half likely tail. That will be our prediction. Okay, we'll talk about that soon, but we focus on pure strategy first. Okay. So this is a famous game. We call coordination game. Okay? This coordination game usually you will see is called stack and hunt problem. Is the two of the agent, okay, can do things independently, can go for a hare, it's a rabbit, right? And they can earn some good money. Here 5 and 5, right? If they go for a small rabbit, okay? Or if they all go for a big animal stack, a big ox, Hi, can you hear me? It seems like it become very weird. Let me switch off this. Is that okay? I hope. I'm using my phone to talk, but hopefully that. Let me switch off this one. Is it? Can you hear it? Can you hear? Oh no, not yet. Okay, okay. I'm using my phone, and I think together it will be okay. So the idea of this is you have two equilibrium, then which one to select is easy. We'll talk about how to select, um, but you really want to say, right, very often we want to say this is the better outcome than this one. Okay. And very often for business, we will either focus on one over the other, saying one is optimal for the firm one or optimal to the firm two or optimal consumer. So it really depends on who has more marketing power, what's the convention. So how to design is actually beyond game theory usually, right? But of course, some people would not say this is good because you go beyond the model, you should model those traditions, right? So that is another other thing. But I think business we are okay, right? Sometimes we just end up in here, right? For example, in network economics, right? If the price are the same, right, you may go to a existing firm, right? There's a convention, right? Suppose the price of you come from the official store in Tianmao or Taobao, right? The same price as some unknown firm, then you probably go to the well-known firm, right? The flagship store, rather than some third-party store, right? So that's the same idea here, right? Because when Bertrand, right, we assume that the tie-breaking rule is going to break in favor no one, right? But in the real world, probably you would favor one over the other. So that is some issue over there, but we don't want to talk too much here. So this one is also a coordinate game, but with some conflict. So this is the game you would play when there's a day without telephone, not too long ago. I mean, a telephone is the time that where you were born, you never know that no time without telephone. I was born in 80s, so I know in the world there's no telephone. Telephone only exists in 90s. Okay, so at least when I was a kid, there's no phone. And so suppose you want to date a girl, right, or boy, then you can't call them, right? So if you do what to do tonight, right, and they can stay at home, right, then basically zero for everyone, right? Then they have to spend their night together, so they have to go to the same place, right? So if one go to football, the other one go to opera, then they can't see each other, then just go home, right? And if they see them in the entrance, they will go there, right? So here we have the model. So girl and boy are the players. Here notice that there's no other boy, no other girls. Okay, only two teenagers. There are no parents here, right? So that's very simple. And the only two places they can go, opera and football. Okay, there's nothing other than that. And the payoff is given by this number. So remember, this already defined the three things: players, strategy, payoff. Okay? And you can easily check these two are Nash equilibrium, and zero are not, right? But these two Nash equilibrium, you can't tell which is better than others, right? You can't say opera is better than football and football. All right. You can say opera is girl optimal, right? It's good for the girl, and this good football is good for boy. Okay. And as I said, very often we will be able to pick one over the other, right? It's a tie-breaking rule, right? So suppose in business, if you have competition between audit firm, then you would think the outcome should be favoring top four over non-top four, right? And if you're thinking about a client and auditor relation, then probably you would think if the client is big, then the client better outcome would realize rather than the auditor one. If auditor is facing a small customer, then the customer will lose, right? So that is something that you can tell which to pick. But you would think the outcome is either they go to opera or they both go to football, right? Rather than going home, right? Going home is not something you would predict. So this is an third game that if you see this movie in the 60s, it's what the chicken game, okay? Chicken in American slang means coward, means that you don't have guts and you're afraid, okay? And people would call each other cow chicken if you're not brave enough. And it's against the game, okay? Whether you dare to do it, okay? So what they do is they would be like this. They would be lying on a line, okay? And there's a one guy, okay, on the motorcycle, okay? And there's another guy as well on the motorcycle as well, okay? Okay? And what they do is to run to each other, okay? They go to each other. If you're chicken, which you're not strong enough, then you turn away, right? Turn your to the other side, right? It's just like run to each other, right? And they go straight. If they all go straight, they die, right? Because the car explodes and then they all die -10. Okay. If you go straight, the other guy chicken, then you win the face, right? And the other just get -2 because lose face. Okay. Imagine this is just a game of a duel, right? Just come together, right? Just everybody hold a knife and come to each other, right? And if you don't run away, then both of them die. If I chicken, the other guy not, then I lose my face. If both of them chicken, then it's okay. If everybody just being nervous, okay. And obviously, this they all die is not, right? They all die is not equilibrium, and they all peaceful is not the equilibrium. Okay, that's why they call anti-coordination game is you want to take the action not taken by the others, right? If other chicken, you want to strike. If other chicken, if other one strike, you want to be chicken, right? You don't want to be same as the others. In that case, you can check the next equilibrium of these two. Why? Because -2, you don't want to jump to here, right? Because you are chicken, but it's better than die, right? And if you're here, it's also next equilibrium because, I haven't checked this one, right? This, you don't want to be chicken as well, right? And if you're straight, the other guy is chicken, you don't want to be chicken, right? Because you're winning already. And the other guy is chicken, don't want to go straight because you don't want to die, right? So there's only outcome is chicken straight or straight chicken. And in this outcome, you can see that neither of next equilibrium are good, right? Actually, the best case in terms of efficient, not productive efficient, which means that they're now you consider this pair of a cardinal, right? If they can pay money to each other, right? Then this is better, right? 0, 0, some of them is 0, the welfare point of view, right? And this is -1, right? This is -20. This is -1, right? In terms of social welfare, which is adding up everyone's payoff, actually it's better to be chicken, right? And also you look at some textbook, they don't do chicken game, right? They will call the hawk-dove game. Is what happened in the evolution is you can be hawk, which is you are very strong, you try to kill each other, you try to attack all the time, or a dove, right? You can imagine hawk is like carnivore, right? You keep eating, keep attacking, very aggressive. Dolphins that you try to avoid conflict, right? Every time you see a big animal, you just run away, right? You don't want to fight. Okay. So this is also a game that well known as well. Okay. And which one is the equilibrium? Of course, will be very similar anyway, right? Because it's just who to be chicken or not. But this will just back and forth as outcome. So next we visit this prisoner dilemma problem. And you notice that the the only Nash equilibrium will be DD. Why? Look at CC. CC deviate to player one want to deviate, right? And player two would want to deviate from C to D, right? The same as here, player one to deviate, right? And player two want to deviate. So no matter what, you will see they all go to DD, right? So but this is Nash equilibrium, and of course this is obviously inferior to this guy, right? You can see CC is always better if they can sustain cooperation there, right? But you can't stop influ, right? You can't stop J, so that's why you get to D. Okay. So everyone worse off is everyone got crazy, right? So now we want to define a term called best response. Why? Because that will help us to find Nash equilibrium more faster. Okay, this is try to dissect Nash equilibrium, and we say a strategy SI star is best respond to a particular strategy by the all other people if S star is better than all other possible thing. That means that SI star is a maximum or the best possible response to SI. Do note that it's a best response is not English, but usually stir because why? Because it's more than one. So although it's not following the standard English, so the best response we don't use the because it can be more than one. Okay, can be multiple. Strategy can be a best response too. So that's why we allow more than one. It's not unique. Okay, so that's why a best response. Okay, once we say that it's more than one, so that's why we will define what we call the best response correspondence. Okay, which correspondence allow us to say instead of a element is a set. Okay, here is we call the beta I. Okay, it's called the best response correspondence facing what other people choosing, right? So this is other people choices. Okay, and we say this is a set means the collection of all strategy that leads to the best response, a best response. So it's a collection of all best response. Okay, so if other people choose S minus I, okay, this is the all possible action that best for you as player I. Okay, so just a notation, terminology. Function is like the following, right? Function is like mapping, right? You mapping between two sets, x and y, right? If you have small x and small y here, right? Dot here, right? Means that for every dot you map to one dot, right? And function require only you that from any dot you map to one dot, can be many to one, can be anything, right? But you don't allow you to do the following. So this is not a function. Okay, you can have two things mapped to one, but you can't have this. Okay? You can't have this mapped to 2 points. Okay, is that clear? this is not a function. This is correspondence. 1 point is not mapped to 2 point. Okay, of course, correspondence simply means a set value function you map to a set, right? It really depends on how we define things, but usually we define this as correspondence, allow you to map more than one. Okay? The set value function, but in math they call correspondence, but it's a set value function, right? So map to more than one element. Once we do that, then simply we can redefine Nash equilibrium. It's called mutual best response. Okay, means that my action is belong to the best response correspondence given what you're doing, and given what I'm doing, your action is also within the best response. So Nash equilibrium can be cleanly written in this one. Okay, given the other guy, my best response is what I'm choosing. Everyone is choosing best given others. Okay, so that is the idea of mutual best response. Okay, there's nothing new here. Okay, why I still want to talk about that? Because that is the idea of a fixed point. Is the math idea. Okay, and Nash equilibrium fixed point is if you write this, okay, and you collect each one, okay, together, we collect the best response for each guy, we can write in this way, right? But this is nothing new, but S1 star, right, is beta 1 S minus 1 star, right? And S2 star is just beta 2 S minus 2 star. Okay. Same thing. Okay, just but write very substantially. Okay, write in a way that is like you give me a strategy, I go to a best correspondence for everyone, you get back what we want. Okay, okay? This is the idea. So that means that we can graphically find Nash equilibrium by finding the intersection of best correspondence, best response correspondence. You will see in the example that is make us to find Nash equilibrium under continuous strategy space. Okay? If this is discrete, it's easy to check, right? You can check everyone, right? But continuous, how can you check, right? The best thing to do is to draw best response correspondence if you're two people. To solve two-person problem, always recommend you to try to find the best correspondence, okay? Because you will not miss anything, okay? Because it include, later you will see, also include mixed strategy equilibrium. Okay. Let me give an example quickly, then we have a break. Okay? Quick example. So I have Carnot oligopoly, N firm, inverse demand. Okay, add together. Strategy is using 0 to Q bar. Q bar means P of Q bar is 0. So it's the maximum people want to pay. Okay, so that is what is said here, right? For everything Q bigger than Q bar, that is 0. But in particular, Q bar is 0 as well because it's a downward sloping. Okay. The cost function given by this is profit function. So there's nothing new on here. Okay. Nothing new here. Okay. So it cannot means that everyone is choosing quantity at the same time, and they take the other people quantity as given when you solve the Nash equilibrium, right? So that means that the correspondence is taking other firm's quantity as given. Okay, you choose the best from you, right? And the equilibrium will be also this minus I here. Okay, minus I here, minus I. So everyone is coming from the best correspondence. Okay, and you can write in this form. So let me draw the diagram very soon. Okay, so let's do this question. Consider the case only two person, linear demand. Okay, linear symmetric cost. So the profit of firm I will be, this is P, right? P of Q, P1, Q1, Q2, right? There's profit minus C, right? Times Q, right? Right. So this is profit margin, right? P minus C minus Q, right? And this is A minus Q1 is the P, right? This is P, and this is C, right? And how do you solve it? Actually, you do the partial derivative, or you can do total derivative, same thing, right? You differentiate this to 0 because you are considering other guys are constant. While you're doing that, you are doing what? Best correspondence, right? We given the other guy's strategy, what is the best for you, okay? And you just take it as a given, exogenous, right? Given this, what you're doing, okay? That's how you solve the partial differentiation, right? And once you solve it, you put this as subject, right? This is what you have, okay? And of course, you also check that because quadratic, this first order condition is indeed the optimal, okay? That's very important. Please do note that you have to check when you write your own model, okay? I mean, even you don't write, you have to write the assumption behind why this is true, right? Although sometimes we don't really care about the SOC, but you have to check, right? Because that can be minimum, right? It's not about worry about whether this is right, but worry about you can't find the minimum. And you get the minimum, indeed the solution will be corner, okay? So it's not about whether the SOC satisfied, because you don't want to embarrass yourself. You actually get the minimum. If it's minimum, the maximum will be the 2n, right? You know, right? Because the maximum always exists, right? In this problem, but don't want to embarrass yourself choosing the minimum. And this is the best response, right? As we said, this is the mutual best response, okay? The one way to do it is just solve this system of equation. Because Nash equilibrium is this belong to this and this belong to this, right? Basically, you have a system equation to solve, which come to this guy, right? Because player 1 is choosing the best given player 2 given best player 1. So that means that we are asking the best response correspondence, okay? And because of this is complicated, usually we would draw a diagram. Okay? So let's draw a diagram here. Why you have this and why you have that, right? Look back. Is A minus C minus, okay, so this is the case. So Q1 is A minus C minus Q2 over 2, right? And similarly, I'm sorry for the color. Maybe I should do it again because I used the blue color for player 1. Player 1 is Q1 A minus C minus Q2 over 2, right? And Q2 is A minus C minus Q1 over 2. Okay. So how can we write this line? I mean, just plot them, right? Let's plot the red one because I'm in the red region already. So when Q1 is 0, Q2 is AC over 2, right? Because when Q1 is 0, it's monopoly. Monopoly is just half of the market, right? That's the best thing to do, right? So this is the outcome here. So this is Q1 is 0. And why but when Q1 is A minus C, basically he produced until the best, there's no price is 0, A minus C, then it's here, right? So this is a less deep line. Okay. And you can do the same for the blue, right? You will do symmetrically. This is A minus C, and this is A minus C. This is A minus C over 2, right? So you have these two lines, okay? And the intersection will be the solution to this problem, right? Because that's what intersection is, right? Is solving the system. Okay? And this system will give you A minus C over 3. Okay. So look, this question is very interesting because if only one firm monopoly is here, right? Monopoly is here. Okay. And perfect combination is here, right? Everyone produces quantity, right? And if you're two firm, they end up here, right? And the production, the industry production is 2A minus C over 3, right? That is more than monopoly, right? Of course, it's less than perfect competition, right? So the two firms together is kind of present dilemma, right? If they can collude a monopoly, A minus C, and they do A minus C over 4, each one, right? If they can collude, right? But they can't, so they end up with a worse outcome, right? Of course, the worst is they end up in here, right? But they don't. Luckily, they don't. But at least when they collude, is here. Is that okay? So this is the Carnot outcome, is the green one. This is monopoly, right? If one a monopoly or this monopoly, right? Either this or this, right? Of course, the best case is the best scenario will be we'll talk about in 2 weeks later. It's possible they end up in this point, which is A minus C over 4, A minus C over 4. And we'll talk about how they can get this point. They share the monopoly profit, the collude. How they can get A minus C over 4. You can't do it in this one shot game. We'll talk about repeat game. If they do interact every day, their way to collude. Okay. The collusion require what we call punishment. Later you will see. If you don't, if we don't do well, then we will end up in worse cases. Okay. By the threat of punishment, we can sustain collaboration. Okay, but we'll talk about that in the we'll talk about next week or the week after. We'll pop up with the game. In that case, we talk about how to achieve this point. This is the goal. Okay, this is the goal we want to achieve. Okay, so collaborate to end up here, right? This is the best case, but because we can't do very well, we can't collaborate. We end up this point, right? So you can imagine this is present dilemma game. We want to go to here, but we end up in this point, right? Everyone can't stop, right? Because everyone, if here, I want to produce more, right? Remember, if you want to be here, if player 2 is here, player 1 will want to produce this much, right? This is the best response for player 2, right? Player 1 will go to here, right? So you can see this, the player 1 produce here, player 2 go to here, right? And you will see it will converge to this point. Okay, the green, this in this particular case, this equilibrium is rather stable, because if anyone deviate, you will end up, the adjustment will likely to end up in the green one. Okay, although we don't talk about adjustment, this is important thing when we talk about evolutionary game theory. There's some way to adjust the dynamics to talk about how to get there. But we just say next equilibrium simply said, if we are here, we're here. We don't talk about how to get there. Okay? We are just saying if we're there, we're stuck there. Okay? We don't talk about if we are not there, someone deviate, what happened. Okay? That can be done. but we are not concerning ourselves at this moment. The paper talk about how to achieve that. Okay, there's some dynamics. That's actually the main thing about macro. Macro talk about the transition dynamics, right? And the starting point is about steady state. Right? But how to get there is another issue. Okay, we just say if we're there, we'll be there. We don't talk about how to get there, right? And in particular, if we are multiple net equilibrium with to pick, we don't say anything. We are silent on those. Okay. Again, that's a break of 15 minutes. I'm sorry, overrun a bit, but let's meet again in 11:15. We cut it a little bit short, but if you learn game theory, it's rather easy. But you haven't learned it, then I go very fast indeed. Because if you go to undergrad or master, they will spend 3 to 4 classes for this. To draw different graphs, to solve different models. But I try to give you a very practical class, but in case you don't know, let me know, because you do the assignment, right? But let's see. Okay, that's a break of 15 minutes, and then we'll see.我现在都用我手机，我手机在给他录，要不然没办法录。下课要打电话的这个，可能要，那几个东西也不行，这个东西不行，可能要把那个麦带下来，把它连一下，因为太，哎，这个房间的不行，这个也不行啊，这个写机也不行，不是什么行的，nothing works. The good thing is close to our office. I just bring my own mic. So then. Time to continue. So I hope that now you kind of see how to solve the equilibrium basically by looking at best response correspondence for this line. It doesn't have to be more than one, but you can see the intersection. And right, in math it's very simple, right? Basically just solve just optimization problem, and each one is solving optimization problem. Right? Just solve. In terms of math, it's nothing new. It's basically before you just solve one guy optimization. Now if everyone is optimizing, just solve the joint optimization problem. Independent. So it's not something like too terrible to solve. Right? You already have that, right? You have a consumer and the problem, you already did that already. Right? But now we have two guys together. Nothing new here. Okay. And let's consider exercise. Okay. Let's do the Bertrand game. Right? I think that's good to quickly do this exercise. Yeah. Okay. What the player said in this Bertrand. Okay. Let's do it together. I suppose to do it at home, but I guess it's good to do it together. So we have 1 and 2, right? Okay. What are the strategy set? The strategy set would be S of 1 and 2, S1, right? Same as S of 2. All right. The price, I mean, you can't set negative, right? So it means that usually just like R plus, right? Or if you like, you can say from 0 to, I mean, there may be some maximum price because maybe P bar, right? Because you can imagine that more than this price, no one will buy it anyway, right? So you can just from 0 to some point, of course, you can do infinity, right? I shouldn't say equal, right? Equal is not a good thing, right? Or this one, right? Or I can write this, right? Or some maximum price. And what's the demand, right? Will be the profit, right? The profit, the U, right? Firm 1 depend on profit from price 1 and price 2, right? Because depend on the prices they're choosing. I use P1 and P2 is price chosen by the thing, by the two firm, right? So the problem is the following. Suppose zero cost of production. Okay. Suppose the market is maybe normalized to 1. Okay. Market size normalized to 1. Okay. So the Q is normalized to 1, right? So if P1 is smaller than P2, I have the whole market, right? So you will be just, I don't normalize because that would be a little bit difficult to see, right? Maybe a non-normalized would be just P1 times Q, right? The size of market is Q. Right? Or maybe to be more explicit is D of P1, right? P1 times D of P1, right? The market. If P1 is higher than P2, then I get 0, right? I don't have anything, right? Of course, the key is what happened if they're equal, right? It's P1 equal to P2. And that I call it P, right? Then the payoff will be this divided by 2, right? Suppose a 2 firm. Okay. So that will be the result, right? And we know what's the equilibrium for this one. Equilibrium will be P1 equal to P2 equal to 0. Right? But that is the setup, right? The only equilibrium you can check, I mean, now with next equilibrium, that's Bertrand equilibrium as well. You can check. The only possible case is 0, 0. There's no other thing you might have. Is that okay? Okay, so you can write down the Nash equilibrium as well. Okay, so that's, I hope that help you to see how to solve this model. Now, let's say we mentioned two solution concepts. One is called the iterated elimination of circuit dominant strategy. One is called Nash equilibrium, and they are related in the following way. If it's more mouthful, is if there is only one remain after the process, there must be Nash equilibrium. That's good. That means that we can always do this operation, okay, without killing any Nash equilibrium. Okay, and we can find equilibrium this way, and every Nash equilibrium survives. Okay, so that means that we can always do this thing without worrying about the problem, right? So basically, what it means is we can shrink our steady set without changing the outcome. If we only care about Nash equilibrium, okay, that's why when I write the Bertrand or Carnot, I can say from 0 to infinity, I shrink from 0 to some very big positive number, right? Because very big positive number is going to be circuit dominated, right, by something else, right? So there's no survive it, right? So it's not shrink it, it's not going to change anything. Okay. But anyway, that's the point. So now we go to a little bit more complicated thing. Actually, go to the next regime, which are now mixed strategy. Okay. Remember this? Or actually, from your experience of doing rock paper scissors, you know there's no winning strategy. Okay. Rock paper scissors is you would expect is you're randomized, right? You don't let other people know what you're doing, right? If you can guess by the others, then you would lose, right? So for this one, there's no Nash equilibrium, okay? Because we already know it. But how to solve this problem is what Nash proposed is more or less you would do mixed strategy, okay? In the sense that now, instead of choosing a particular strategy, you are choosing a probability distribution over strategy, okay? You'll be a strategy that is mapped to a simplex, 0 to 1. You give a probability distribution, okay, over the strategy set, okay? And that is why we denote as a simplex over this your strategy space, okay? But there's a cost of doing it because we are randomizing, right? And how to evaluate your strategy would have to depends on uncertainty, right? So that's why you don't know what the other guys is doing, okay? And you're randomizing only by yourself. You have your own randomizing device. You toss your own coin, right? Everyone have their own coin to be tossed, okay? But then you evaluate Nash equilibrium later. You will see you do the payoff, right? The payoff depends on what is being realized, right? And that's why when we study last class, we need to study expected utility, right? Because what outcome may realize depend on nature, right? So that's why utility for a particular strategy, it depends on the product of that particular strategy comes out times utility of that. Okay. So this is definition is you choose S, right? Everyone choose S. This is the payoff. And this is probability you get S. Why this product? because this is independent. Everyone has their own dice. Everyone has own randomization device, random, and then it's a product, right? Because probability of S is probability of S1 times probability of S2 and times probability of Sn, right? And why the joint can be equal to product of marginal that is coming from independence, right? Say, for example, let me give example why to make sense of this, okay? If you randomize this by 1/2 and 1/2, the other guy's also 1/2 and 1/2, okay? What is the probability to get this one? Okay? If it's independent, this outcome is just product of this marginal, 1/2 times 1/2, right? That's what you learn in the probability class, right? The product of the joint is product of marginal if they're independent, right? And because your randomizing is independent, it's not, there's no public device, okay? They're not looking at the sky. When the sky is bright, I do this. When the sky is blue, I do the other thing. No, right? They're not looking at the same sky. They look at their different device. They have pros and cons privately, so independent. And in that case, the probability that S being realized is product for each guy multiplied together. Okay, so that is what I said. Okay, is that okay? And do note that this is a expected utility that sometimes we call von Neumann-Morgenstern utility. Okay, and and this is the payoff. Okay, so I use the capital U instead of small u. Okay, and mixed strategy require you the same thing. Everyone keep their mixed strategy rather than other thing. Okay, so that's the best response in terms of mixed strategy. Okay. Is that okay? So let's solve this game. So solving this, and then we'll call it for today. Okay. Done. This is the last game we do. I know if you haven't learned game theory, there's a lot for you. Okay. You've learned it, that is too simple. Okay. But I only can strike balance between you know and you don't know, right? So I'm sorry. I mean, I make no people happy. It's a Pareto inefficient outcome. But that's the best I can do. Okay. Although it's not the best case. Okay. So here again, we have two players. Okay. And the red and the blue means the strategy set, right? And the green will be the payoff function. Okay. Now we allow our strategy, not just pure strategy, we allow mixed strategy. We allow to assign probability over head or tail. Okay. That means that the S is still head or tail, but our strategy is a probability distribution. Okay. We put some probability over H, some probability over tail. Okay. Same for player 2. Okay. That means that MIH plus MIT will be equal to 1. And luckily, we only have 2 outcomes. Okay. The probability or over 2 outcomes can be represented by a number, right? You can just focus on the 1, the other will be 1 minus. Okay. So I call this R, this 1 minus R, right? And this call it Q and 1 minus Q. Okay. So that means that I reduce this to one-dimensional problem, right? Player 1 is choosing an R, player 2 is choosing just Q. Okay. Is of course R is the continuous variable from 0 to 1, and Q is from 0 to 1 as well. Okay. So I just simplify the problem in a manageable manner, right? You can imagine that the complexity increase significantly if I allow more than 3 strategies. allow free strategy, right? Because free strategy, I have to maximize over two numbers, right? So it is not that easy, okay? But once you have that, let's see how we solve this problem, okay? You can immediately see the model become crazy already, okay? I try to solve this, okay? How do you do that? Remember, it's like this. They are the maximizing the expected utility, right? So we have R here, 1 minus R here. We have Q here, 1 minus Q here, okay? If I adopt this strategy, what's the payoff for player one? This outcome comes with probably R and Q, right? So the payoff is -1. So the payoff for this outcome is -1 times RQ. Okay? And you have another outcome, which is this, with probability R times 1 minus Q, right? But the payoff is 1. So it'll be 1 times R times 1 minus Q. Okay. You can do the same for the rest. This, right, will be 1 times 1 minus R times Q, right? This, you can go on like this. Is that okay? Okay. And the rest, the last one will be, okay, this guy, right, which is -1 times 1 minus R times 1 minus Q. Okay. So if you do this, this will be the 4 different scenarios you can see, and this pay off your expected utility. So you just, each scenario, you just take it out, right? So that's what you get is this complicated object, okay? But calculator will easily convert to this one, okay? It's 1 minus Q, 2Q minus 1, and 2R minus 1, and minus. Okay? So remember, player 1 is using R. So player 1 is using R to maximize this guy, okay? Of course, you can do calculus, okay? Because it's a single variable. And you differentiate respect to R, okay? Okay. It's -2, okay? Because this is a constant, right? Q is constant, right? You are maximizing giving other strategy constant, right? Because you're finding the best correspondence. For every possible strategy the other guy is choosing, you're optimizing, okay? That is the best correspondence. How do we find that, right? Is maximize is partial derivative, right? You figure out that this outcome is independent of R, right? And that turn out that, and this is positive negative depends on whether Q is more than 1/2 or less than 1/2, right? If Q is 1/2, this is 0, okay? Means that what? If Q is 1/2, it's always 0, means regardless of what R is, optimal, right? Anything is optimal when Q is 1/2, okay? When the other guy is randomizing, you don't care what you're doing, right? If the other guy is your player 1, right? The other guy is randomizing of head or tail, you doesn't really matter what you do, right? Because you want to be different from him, right? Your player 1, you want different. And if Q is less than 1/2, right? It's more likely to be head than tail, right? Then what you're going to do, this guy is negative, right? 2Q minus 1 negative. It's positive, right? This all positive means that you want R to be as big as possible, right? Which means what? Which means that we want head. Why? Because Q is less than 1/2, which means that the other guy have more tail than head, right? You want to be different, so you want more head than tail. You want most of the time is head, 100% time is head. Don't want head, right? Reversely, if Q is bigger than 1/2, which means that the other guy is more likely to be head than tail. Your player 1, you want it different, right? So you want to tail 100% tail, right? That's shown in here because negative. So you want this to be as small as possible. how low you can go? R is between 0 and 1, right? So go to 0. So that's what you get. In the next slide, I show you the optimal is like this. Okay. When it's 1/2, doesn't matter. When it's less than 1/2, it's 1, right? Because the other guy is choosing tail more likely, you will choose head. 100% head. Similarly, if the other guy is randomizing, more likely to be tail, surrounded to head, then you want to be tail, right? So actually you can draw this guy. This is your best response correspondence. The correspondence, because this is not a single number, you allow yourself to choose between 0 to 1. Okay, let's draw this picture, and you will see how we can solve this problem. This is what you draw. Okay, this R, this Q. Okay, your player 1, I should use red color. Okay, your player 1. Remember, if the other guy choosing the Q is 1/2, you don't care. So that's why you have this line, right? This line is saying that you don't care when the other guy choose 1/2, right? If the other guy more likely to choose head, which is here, you would choose tail, right? Which is 0, right? If the other guy choose more likely to get the tail, you would choose head, right? So this is the tail, this is head, right? And if this is, doesn't really matter to you. Okay. And you can do the same for player 2. Okay. Player 2 turned out to be actually what is a zero-sum game, which means that the payoff for player 1 and player 2 add up to be 0 because one paid the other, right? So that's why you don't need to do anything but just take away the negative sign, right? Because what is gained for player 1 will be lose for player 2, right? The error must be 1 because there's nothing, there's no outsider. And you can do the differentiation because they're choosing Q, because this is here, this Q is 2, right? And obviously the same, if R is 1/2, always 0, the Q, anything is fine, right? If R is more than 1/2, means that player 1 is more likely to choose head, then you will choose head as well because you want to be the same, right? Because player 2, you want the same as player 1. So that's why more than 1/2, then you get 1 here. You choose head as well. If the other guy is player 1 is choosing more likely to choose tail, you also choose tail as well, right? So that's why you get you can draw is like 0, anything 1, right? There's a 0, anything, and then 1, right? See, right? If R is between 0 and 1, then 0 and 1/2, then it's 0. It's here, this point. Otherwise, it's here, and it's 45 degrees, right? So this is the only outcome, is both of them are randomizing equal likely head over tail. Okay. So you can see I solve it in this manner, and this manner I will not miss any equilibrium. Okay. So I expect you, if you will do it seriously, this is the way to solve, right? Because this is starting from the first principle. You look at the best response of each agent, and you look at the intercept, and this is the only way, and you need way to solve it. Okay. And probably sometime in your undergrad, if you ever learn it, they don't tell you this way. You'll be learning the other way, which we will mention next class. But this is the only way that you should solve this problem. Okay. In this one, it's very simple. You just have only one outcome. And after next week, we talk about vector of sex. You will see you have 3 possible solutions: 2 pure strategy and 1 mixed strategy. And by doing this, this is the way that you can figure that out. Is that okay? Okay. So I think I should end here. Next class, we will continue a little bit of the remaining slide. Then we're done with the game theory first part. Okay, we will do the after that we do dynamic games and and then we'll do incomplete information. Okay. And I think I will hand my time to our TA, who will talk about your assignment. I don't know if she want to use the screen or she want to do it not. Okay. Let me right screen view. Oh no. So again, it's optional. So if you want to, you're busy, you want to do something, you can just you don't have to remain. It's okay. Can just talk. Yeah. Maybe just you can log on the Zoom. Easy. They can share. No, I can just.
So maybe I can talk first. So let's start our second tutorial. In second Q, we cover two topics: the producer and behavior. So, for the first question,